Hello everyone. In this session, I'm looking at comparisons of the means and the median of a sample of data with some kind of hypothesized value. Right? We have taken a sample. Based on that sample, we want to find out whether the mean of this particular sample is more or less equivalent to a hypothesized value, or is it significantly different from that. So we are taking one single sample at a time and trying to find out whether the mean of that sample or the median of that sample is equal to some specific value, right? So we are taking a data set. I want to take it practically. We are taking a data set. The data set is taken from the world of finance, especially the stock market returns, but again, it's just a data set. You can use it in any field. You understand the context of the data, that will help you to use this test in almost every field, whether it is marketing or HR or operations or pharma sector or any such kind of sectors, healthcare, etc. Now, I want to make some kind of tests or conclusions with respect to the mean of a data or the median of a data. That is where I am referring to these kind of tests, right? So here I am talking about three types of tests. One is a t-test for a hypothesized mean. So I am hypothesizing a particular mean for a particular data, and I want to see whether the sample that I have taken and the mean that I am computing from that particular sample is more or less equal to this hypothesized mean, or is there a significant difference between the hypothesized mean and the mean that I got, the mean that I have got through the sample. Similarly, we are talking about a Wilcoxon signed rank test. This is primarily for comparing the median of the sample with a hypothesized median value. The same logic goes for the usage of sign test also, where I am using a hypothesized median, trying to compare the sample's median with the hypothesized median. So here I am simply taking a data set, which, as I have already indicated, it's a monthly returns of the various sectors on the Bombay Stock Exchange BSE. Of course, for this purpose, I would be using only one sector, right? Because we are more interested in one variable at a time. So I would be more interested in taking only one of those 11 sectors that I have captured in the data. So this is a very small example, right? Even the test is not a complicated test. We are only comparing whether the sample mean is equal to a hypothesized value or the sample median is equal to a hypothesized value. That's it. There is not much of a complication in the tests that we are doing. Probably some of the preliminary tests that we have to do in our data analytics process. So getting started, before that, let me load the data. Right, this is the data which is there in this particular folder. This is the CSV file that I have. Quickly looking at what is there as a part of this index red. It's a monthly return that we right from 2007 February to 2016. If I look at the tail data, you will get the ending point which is clearly saying that you have the data until the December 2016. Right from February 2007 to December 2016 is what is the data? 119 rows, so approximately 10 years of data. And these are all the monthly returns of all the sectors. Telecom sector in February 2007 has given a loss of 2.2%, whereas in March it bounced back to a positive 7.3% return, and in April again it has gone to 8.8% return, and so on. That's the way you can interpret all the various sectors, right? Right from 2007 to 2016, how the monthly index values have changed during the period. So with this as the data, now I want to take one sector at a time. Let's say, let me take only the telecom sector for time being, and I want to use, so probably let me that out, right? I'll simply call telecom as another variable, wherein I'll take index rate dollar telecom. So I'll take that telecom sector's values as a separate variable. So this is the 119 values of the telecom sector. Now let me try going ahead with all these tests. Initially, we are starting off with a one sample t-test for a hypothesized mean. So I am simply making the test is primarily, I want to really find out if the mean of the sample that I have chosen is significantly different from a hypothesized mean. So in this, I want to take, is the monthly return, right? Is the monthly return on the telecom sector equal to 1%? So between 0.01. So the hypothesized mean, I will take it as 0.01. And I want to really compare whether the mean of the sample is significantly different from the hypothesized mean. So this is where I am doing a comparison of a sample mean to a hypothesized value. Sample mean comes from the 119 observations that we have, and the hypothesized mean we have taken in this case is 0.01, which is 1%. So the null hypothesis here is, so for every of these tests we have a null hypothesis and we have an alternate hypothesis which is exactly opposite to that of the null. So sample mean is not significantly different from the hypothesized mean, which means the mean of the sample is equal to the mean of whatever you have hypothesized. Whereas the alternate hypothesis says no, these two cannot be equal. So mean of the sample is either greater than, significantly greater than the hypothesized value, or significantly lesser than the hypothesized value. But of course, let's understand that this test is having some level of validity only when your sample observations are normally distributed. For this, you have so many ways of testing whether the data is normally distributed or not. You can find out the skewness and kurtosis of the data. See if the skewness and kurtosis, both of them are very close to zero, then you can very well say that your data is normally distributed. Otherwise, there may not be a case of normal distribution. But of course, here I am not doing that test. So, assuming that the data is normally distributed, I can go ahead with the one sample t-test. And also under the other assumption that the population standard deviation is unknown, I have to find out the standard deviation from the sample itself. Under these two assumptions, I can very well go ahead and implement the one sample t-test, which comes from the base package itself, where I use a function called t.test. So I'll be using this t.test function. Let me see what it is doing. It's a very simple function. Performs 1 and 2 sample t-tests on vectors of data. I need to give a vector of data. That's the reason I have split that column data into a vector. We have got everything into a variable called telecom. So either one sample t-test or two sample t-test. Two sample t-test, I'll take care of it in my next session. But right now one sample test is what we are performing, and simply I have to give t dot test. That's it. And alternative, I can give either two-sided, less or greater. So what does that mean? If the alternative is two-sided, then it means my null hypothesis is sample mean is equal to population mean or the hypothesized mean, and the alternate hypothesis is no, they are not equal, they are different, means it could be lesser or it could be greater. Whereas if I say the alternate hypothesis is less, then the null hypothesis is not just equal to, it could be greater than or equal to the hypothesized mean. Whereas the alternate hypothesis will be lesser than the hypothesized mean. Whereas when I am setting greater, the null hypothesis says the sample mean is less than or equal to the hypothesized mean, and the alternate hypothesis is the sample mean is greater than the hypothesized mean. So depending on what I have said, this pair of null hypothesis and alternate hypothesis will be chosen. So let's go with the two-sided itself. I have to specify the mu value. Mu is what is your hypothesized mean. I have to give that mu value. Paired equal to false. Of course, only when there are two variables, the meaning of paired will come into picture. Here we are talking of only one variable, so we don't have anything to talk about them. The same goes with variance equal or unequal. Again, all of them will come into picture only when we are talking of two variables. Confidence level is something that I can very well take, which gives what is the 95% confidence interval of the difference in the means of the two groups. Right, I am talking about what is the mean difference between the means of the two groups versus mean difference between the hypothesized mean and the sample mean, and even the 95% confidence interval of that difference also will be considered. So let me simply take this t dot test. Initially we are going with only a one sample step, so we don't have a second sample at all. So first I have to give my x value, which I'll give it as telecom. Then alternative, let me take it as two-sided, means the null hypothesis is the sample mean is equal to population hypothesized mean, whereas the alternate hypothesis is the sample mean is not equal to the hypothesized mean. It could have been greater or lesser than the hypothesized mean. That is the alternative being two-sided. Then I have to give my mu value. We have set it as 1%. So let me put it as 0.01. That is the mu value that we are setting. And I am also interested in looking at the 95% confidence interval for the difference. So straightforward test, you could see it's a one sample t-test. There are some calculations that are being performed, the t value, the degrees of freedom, but I am more interested in the p value. P value is 0.1112. Right, p value in this case came out to 0.1112, which is greater than 0.05. So I cannot reject the null hypothesis. I have to go with the null hypothesis itself. A null hypothesis says that the sample mean is equal to the hypothesized mean. It's not significantly different from the hypothesized mean. So on an average, I see that the telecom sector is giving a mean of around 0.1% or 1% per month. If you look at actually the numbers, it is minus 0.32%. That is what is the average value from the sample. But the 95% confidence interval said that that number could be anywhere between minus 1.959% to 1.30%. And that's the reason 1% is lying very much in this interval. So there is no way I can reject this null hypothesis. So that's the reason I don't have solid evidence to reject this null hypothesis of 1% return. So I am fairly assuming that there is a possibility of getting 1% return. I cannot reject the null hypothesis at 95% confidence level. So this is the typical interval. So I can say with 95% confidence that the monthly return of the telecom sector could be between minus 1.96% to 1.3%. So that's how the telecom sector's returns have been with a 95% confidence level. Right? So that is what we are able to interpret. The overall average is minus 0.32%, but the interval is saying anywhere between minus 1.96% to 1.30%. Now, this assumes that the distribution is normally distributed and the population standard deviation is unknown. Now, the next test that we are looking at is Wilcoxon signed rank test. Especially, it's a kind of an alternative to the t-test that we have performed just now. Instead of looking at the mean, this focuses more on the median. Right? Is the median of a sample significantly different from the hypothesized median? It's a good alternative to one sample t-test. Especially when your data is not normally distributed, you find that the data is very heavily deviating from normal distribution. Then you can very well look at going ahead with Wilcoxon signed rank test, which is an alternative. Instead of comparing the mean with a hypothesized mean, it will compute the sample median with a hypothesized median. So again, the null hypothesis says that the median of the sample is equal to some kind of hypothesized value. Whereas when I'm going with the two-sided test, I can very well take that the median of the sample is not equal to the hypothesized value as an alternate hypothesis, and I can very well say that the median is either greater than or lesser than the hypothesized value. And let me tell you here, there are no assumptions regarding the distribution of the data because this comes under the category of a non-parametric test. So regarding the sample distribution, it is making really no, and no assumptions are typically made regarding the distribution of the data. And this can be executed from Wilcox.test function, exactly from the same stats package. Wilcox.test is actually performing the one sample Wilcoxon signed rank test. Right, so let me first do the question mark of this. So performs 1 and 2 sample Wilcoxon tests. Again, when we are talking about 2 samples in the next session, I'll come back to it. On the vectors of the data. The 2 sample one is typically called as Mann-Whitney test. When I talk about it in the next session, I'll use the name. But when I'm using it in the 1 sample category, it is nothing but it's a Wilcoxon test. Now, all I have to give is exactly the same. If you look at Wilcox.test, I need to take the x value, only one variable I am considering. My x in this case is telecom. Then if you see y, I don't need because y will be coming into picture only if I have 2 variables. Alternative, I can still go ahead with two-sided itself, which says the null hypothesis is median of the sample is equal to the median of the hypothesized median, and the alternate hypothesis says no, these two are not equal. It could be one could be greater than the other or lesser than the other. Then again the mean, which is the mu equal to, which is the hypothesized median. Even the hypothesized median also, let me take it as 0.01 itself. Confidence level, right, the confidence interval is coming out to be false. Confidence level, I can very well set it 2.95 and go ahead with the computation of the same. And if I want, I can even set the confidence level, confidence interval as true. and I can go ahead with the generation. So it is talking about a Wilcoxon signedrank test with continuous correction. The p-value here is 0.2312. That is what is more important for me. The p-value is 0.2312 greater than 0.05. So I cannot reject the null hypothesis. I have to take my decision in favor of the null hypothesis, wherein I can say that the sample hypothesized sample median is nowhere significantly different from the hypothesized median. And it's also giving that the 95% confidence interval for the same. Overall, the sample median is around 0.04%, but the 95% confidence interval is saying it is minus 1.524% to 1.624%. So which includes the 1% in this range, and that's the reason the null hypothesis cannot be rejected at 95% confidence level. So based on that, I can very well say that whatever is the sample median that I am getting, it's nowhere significantly different from the hypothesized median of 1% per month. So that's how I can use the one sample Wilcoxon signedrank test. Then I can also use for the same similar objective, I can also use sign test. Everything remaining the same. I am looking at a median of a sample significantly different from hypothesized median. It can be used as an alternative to one sample t-test when the normal distribution of the data gets challenged, or in some cases I can use it along with the Wilcoxon signedrank test, which is a non-parametric. Even this is a non-parametric test which will which will compare the sample median with a hypothesized median. It will not look at the mean or any other stuff. But the thing is, you can very well get it from two different implementations. One, you have a using R package from which I can use simple.median.test function, or you can use a BSDA package wherein you are taking sign.test function. Either of them should give you the result for the sign test. So let me use using R package. Right, I am using the using R package. So there are a lot of dependent packages. So all of them are getting installed for our further sessions. This would simplify the whole installation process, because lots of packages are already getting installed for this purpose. Okay, now that the packages are installed, let me load the package using R. The package is loaded for me, so I need to use simple.median.test. So if I look at it, simple.median.test, find out the help relating to it. It does simple sign test for median, no ranking. So it does simple sign test like a Wilcox dot test without the ranking. This computes two-sided p-value No confidence interval is given. Only the p-value is what comes out of this. So I can simply say simple median test. I just need to give these two values. That's it. Wherein I have to give my x. The x in this case is telecom, and the median value, as we have looked at in the earlier case, I am setting it to 1% or 0.01. That's it. It gives me the p-value, which is 0.199 greater than 0.05. I cannot reject the null hypothesis, so I am taking my decision in favor of the null hypothesis, saying that the sample median is not significantly different from the hypothesized median. That's it. It's only one single interpretation that we are getting from the simple median test. Similarly, I can go with a BSDA package and go ahead with Sign.test. test. So even if I do the BSDA package, alright, library, I do a BSDA. Now again I go with the Sign.test. That's it. Let me just see what is there in that BSDA package. Okay, basic statistics and data analysis is the name of this package. Let me see what is there relating to sign. Oh, SI all in caps, sign.test. So let me come back. Sign.test. If I'm looking at it, this function will test a hypothesis based on the sign test and reports linearly interpolated confidence intervals for one sample problem. So I'm giving as x, which is a numeric vector. NAs and infinites are allowed, but they will be removed. Y I don't need to give. It's an optional numeric vector. MD is the median, right? What is my hypothesized median? I have to give that. Alternative is by default it is two-sided, but I can very well give the greater or lesser. We have discussed about what those alternatives mean. And confidence interval, by default I get the 95% confidence interval. So I can simply take this sign.test, right, and here I need to specify some of the things. The median value, the hypothesized median, instead of 0 I will take it as 0.01, which is 1%, and x value I will take it as telecom, y I can leave it as it is. Now this is slightly a better representation. The p-value is still 0.1992, which I have got even when we have used the simple median test, but in the simple median test I get only this, nothing else. Whereas here we are seeing that the p-value is 0.1992. Yeah, I will also get the sample median value, which is around 0.03%, and from where it also went to a 95% confidence interval, coming out to minus 2.01% to 1.45%. That's the 95% confidence interval. And if we are looking at the lower achieved confidence interval, it is 0.9337, which is working out at an interval of 1 point, minus 1.89 to 1.33%. And similarly, upper achieved is from minus 2.07 to 1.51, and it got interpolated, finally working out to minus 2.01% to 1.46%. That's how the interpolated value got computed for us, and that's the typical 95% confidence interval for this hypothesized median. And since our target was 1%, let's say instead of 1%, I set it to 2%, I would very well get a different figure altogether. When I said the median, hypothesized median is 2%, I could see that the p-value is 0.99%, which is lesser than 0.05 or 5%, which means I have to reject the null hypothesis, taking my decision in favor of alternate, saying that the sample median is not equal to the population median or the hypothesized median of 2%, because the 95% confidence interval is in this range. What I have specified is beyond the range, so the null hypothesis gets rejected. So that's how we can understand the one sample test for comparing the mean and medians of a sample to some hypothesized values. So that's what I wanted to take as a part of this session. If you have any further queries regarding the same, you can very well get in touch with me by giving me a call on the number that I have given below, or you can even send in an email at the email address given below. Thanks a lot for listening to this session. Thank you very much.